Welcome to The Explainer. Today, we're diving into something truly mind-blowing. We are going to unpack one of the most incredible mid-century engineering feats in human history. We're talking about the insane story of conquering impossible geology to literally sink a high-speed transit tunnel directly beneath the ocean floor. It is a story packed with incredible vision, high-stakes problem-solving, and honestly, structures so massive they almost defy logic. Okay, let's dive into this. To really grasp the magnitude of this project, you first have to wrap your head around the sheer scale of the geographic roadblock separating San Francisco and Oakland. We are talking about 3.6 miles of open water. Now, today we might take crossing that gap completely for granted, but mid-century, that 3.6-mile stretch of the San Francisco Bay was a massive isolating barrier, and it was threatening to completely choke off the entire region's economic growth. Because, picture this. By the late 1950s, the Bay Area was facing a full-blown traffic crisis. The San Francisco-Oakland Bay Bridge was absolutely choking on cars. Every single morning, you had tens of thousands of commuters desperately trying to squeeze across this one single strip of asphalt just to reach San Francisco's financial center. It was a mess. The region desperately needed a high-speed transit network capable of moving tens of thousands of people per hour. But here's the thing. Building another bridge just wasn't going to cut it. They had to go under. But going under, that meant facing an absolute geological nightmare. If you look at what actually lies beneath that water, well, it isn't solid bedrock. Nope. It is deep, deep layers of super soft sediment, basically known as bay mud. And to make matters infinitely worse, this unstable ocean floor is sandwiched directly between two of the most active fault lines on planet Earth, the San Andreas and the Hayward faults. You're essentially trying to build a stable transit line through a giant bowl of jelly sitting right on top of a massive earthquake zone. So the Engineering Dream Team, a joint venture known as Parsons Brinckerhoff Tudor Bechtel, they take one look at this and realize something pretty quickly. Traditional tunneling, using massive boring shields to drive deep through solid underground rock, that was practically impossible in that deep, soft mud with 1960s technology. So they were forced to make a radical strategy pivot. They went with the submerged tube method. Instead of digging a tunnel underground, they decided they would build the tunnel on land, float the pieces out into the water, and literally drop them into a pre-dredged trench right on the bottom of the bay. So the crucial point is how they actually designed this thing to work. They came up with what's called the binocular design, and you can probably guess why. The footprint looks remarkably like a giant pair of steel binoculars. This layout gave them two main bores for the high-speed train tracks, separated by a central utility corridor. And that center space? It's brilliant. It functions simultaneously as a safe pedestrian walkway in case of an emergency and as a vital ventilation shaft. All of this is packed into a massive footprint that is 48 feet wide and 29 feet high. Now, we aren't talking about small, easy-to-handle pieces of steel here. The awe-inspiring scale of the individual structures that had to be maneuvered into place is just hard to wrap your head around. Each individual section was roughly 330 feet long. That is literally longer than an entire American football field. Just take a second to imagine trying to maneuver a hollow steel football field through the treacherous chopping currents of the San Francisco Bay. By 1965, construction is officially underway. A total of 57 of these massive steel shell sections were fabricated at Bethlehem Steel Shipyard right there in San Francisco. But how do you get these giant steel leviathans from a dry shipyard out into the water? Well, workers welded the hulls together and then did something incredibly simple yet totally ingenious. They sealed both ends with temporary wooden bulkheads. That temporary wood trapped the air inside, making these massive steel structures buoyant enough to actually float. And this is where we get to this incredibly tense underwater industrial ballet. Heavy tugboats would tow these floating hulls out to a specialized placement barge in the middle of the bay. Meanwhile, giant dredges had already dug a trench up to 135 feet deep into the bay floor, laying down a perfectly leveled gravel bed. To sink the 10,000-ton steel giant, engineers started pouring thousands of tons of concrete into the hollow spaces between the inner and outer steel shells. As the weight increased, it slowly sank, and to make sure it landed perfectly, crews guided the section into position using laser guidance systems, which, by the way, was absolutely cutting-edge technology for the late 1960s. They were dropping a 10,000-ton section onto a gravel bed with mere inches of tolerance. It is wild. Once resting on the bottom, undersea divers went to work. They used hydraulic couplers to lock the newly dropped section to the previous one. Then they simply pumped out the water trapped between those temporary bulkheads. The genius here is that the immense atmospheric and water pressure from the bay itself actually helped push the joints incredibly tight, creating a continuous, perfectly dry tunnel. Finally, the entire structure was heavily backfilled with concrete, sand, and this super heavy gravel armor. That armor is crucial, by the way. It protects the tube from dragging ship anchors and really intense tidal currents. But we've got an elephant in the room here. You can sink a massive steel tube in a calm bay, sure. But what happens when you lay a completely rigid tunnel across soft, shifting mud, and then hit it with a magnitude 8.0 earthquake? The answer is terrifying. It would easily just snap under the extreme multidirectional seismic stress. The engineers knew from day one this was their ultimate do-or-die hurdle. Now, what's really interesting about this is how they tackled that exact nightmare scenario. They engineered an absolutely ingenious solution called sliding seismic joints. At both ends of the tube, right where it connects to the rigid solid land structures of San Francisco and Oakland, they installed these giant universal ball and socket mechanisms. These joints are an absolute marvel. During a massive earthquake, they allow the entire tube to pitch, roll, and slide up to several inches in absolutely any direction without ever rupturing the waterproof seals. Basically, it gave tons of concrete and steel the one thing it desperately needed to survive: flexibility. For years, this brilliant engineering fix just sat quietly in the mud, completely untried. But then, on October 17, 1989, the ultimate test arrives. The devastating magnitude 6.9 Loma Prieta earthquake violently strikes the Bay Area. This was exactly the real-world, high-stakes, doomsday scenario the engineers had designed for. And honestly, nobody knew exactly what they would find when the shaking finally stopped. And the contrast in the aftermath, it was absolutely staggering. Up on the surface, it was complete devastation. A massive section of the Bay Bridge actually collapsed, and complex highway structures completely failed all across the region. But 135 feet underwater, the Transbay Tube suffered zero structural damage. None. The seismic joints performed flawlessly. In fact, the trains inside were back up and running within hours, serving as the sole critical lifeline that kept the Bay Area connected during one of its absolute darkest hours. When you really stop and think about it, the everyday miracle this structure provides is just wild. When the tube first opened for revenue service back in September 1974, it instantly transformed a grinding, unpredictable commute into a breezy, incredibly reliable trip. It cut the travel time between downtown Oakland and downtown San Francisco to just under 8 minutes. 8 minutes! 8 minutes to cross a geographical divide that used to dictate the entire pace of the region. And this brilliantly illustrates why continuous investment in our infrastructure is so vital. Today, more than 50 years later, the tube remains the single most critical transit corridor in Northern California. But thankfully, they aren't taking its past success for granted. To make sure it actually survives the next big one, a multi-year earthquake retrofit was recently completed. They went in and installed massive internal steel plate liners for extra rigidity where it was needed, and added ultra-high-capacity pumping systems to handle unprecedented water intrusion. They are actively making sure this mid-century marvel is totally ready for a 21st century disaster. Let's zoom out and see how this all builds together, because it really paints a complete picture of an infrastructural triumph. We started back in the 1950s with this paralyzing traffic crisis. By 1965, fabrication of these massive steel football fields begins. In September 1974, revenue service completely revolutionizes the Bay Area commute. And then, in October 1989, it proves its worth by surviving the Loma Prieta earthquake without a scratch. This timeline represents a silent masterpiece of civil engineering that tirelessly keeps the Bay Area moving every single day. Which leaves us with a pretty fascinating thought to take away from this explainer. The San Francisco Bay was basically an impossible barrier, filled with treacherous mud and flanked by deadly fault lines. Yet, human ingenuity found a way right through the middle of it. It really makes you wonder, as you look around at the major bottlenecks and geographical hurdles of our modern world, what impossible obstacles are out there right now, just waiting for the exact right engineering solution? Keep that in mind next time you travel. Thanks for exploring with us, and we'll see you next time.